Hello.
Hi.
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 Hi. Took me a while to get on here. My Wi-Fi is not behaving very well.
Oh,
So if it dies midstream, that's why. Either that or I've given up. All right. Um, so let's get started. All right. How's everybody? Coping?
Good.
Good. How are you? Yeah.
All right. Good. Had a couple nice days of weather here.
Mhm.
Now it's going to rain for a while, but that's life. All right. So in our last episode, we were talking about Probit and Logit. And so we had done some estimation of Probit and Logit and established that we can't just look at coefficients to read them. We need to transform them into marginal effects. And it turns out that there are several ways to do that, several different kinds of marginal effects that we can find. And also it's the case that the value of one variable affects the marginal effect of a different variable, of other variables. So the variables all interact. And this makes interpretation, we can think of it as just more complicated, or we can think of it as an opportunity to learn more. Let's see, let me pull up my Stata screen. Here we go. And yeah, so we were using the MROS2 data set. And we had, I don't remember exactly what the regression that we had estimated was. In labor force is a dummy variable, and that was our dependent variable, whether or not a person is in the labor force. And so we had done something like in labor force as a function of number of kids less than 6. So these are married women in this data set. Woman's age, her, let's do this. We'll use her educational category. And so this is a, I don't know if you remember what this variable is. Let me go back and talk about that variable. So that's just a variable that I created, which is 1, if the person's education is less than high school, 2, if they have a high school graduate, 3, more than high school, 4, bachelor's degree, and 5, graduate work, more than a bachelor's degree. Okay. Now I'm going to use this variable in the regression. So I'll go back, Probit in labor force as a function of kids under 6, her age. And for this variable, when we have a categorical variable like this, we've done this before just using separate dummy variables. And that's really what we want. But we can use this variable, call it, just say I dot, and Stata will separate it into separate dummy variables. And there's an advantage to doing this, and I'll show you the advantage after we do the regression. Okay, so first of all, it's a little bit more compact just in terms of writing it. And Stata will simply split this into a bunch of dummy variables. And what else do we want to put in here? We'll put in family income and experience, and that's good enough. All right, and so you can see that Stata splits this up into dummy variables. It just drops one category automatically. When we look at this, we could do this likelihood ratio test is that's analogous to an F test in ordinary least squares. They test the hypothesis that all of the coefficients are 0 against the alternative that at least one is not. We reject the hypothesis that they're all 0. All right, and so we have these coefficients which we can't interpret directly. And so maybe what we would do is to want to find the marginal effect. And so the first thing we'll find is what's called an average marginal effect. Okay. And we find that by typing margins and then dy dx. And we indicate with the star that we want to apply it to all the variables. You back? Am I back?
We're good.
Hey. I don't know what's going on with my Wi-Fi. All right, so let's see. So we have these marginal effects, and these are average marginal effects, which means that it is giving us the average effect over all values of all the variables, the average effect of each independent variable on the probability of being in the labor force. So this says that number of kids less than 6, as that increases by 1, the probability of being in the labor force goes down 27%, by 0.27. The older you get, every year older, the probability of being in the labor force goes down by about 0.02, 2%. Probability of being in the labor force looks like it increases with each level of education. There's a positive effect of family income, though it's really not statistically significant. And the more experience you have in the labor force, additional year of experience increases the probability of being in the labor force by about 2%. Okay, so those are average effects, and those are perfectly useful ways to describe the effect of the independent variables on the probability that the dependent variable is equal to 1. Okay, any questions about that?
Professor?
Yeah.
Are we holding all the others,
Yes.
all the other independent? Okay.
Yeah, they're all held constant. These are all partial effects. You know, I showed you the other day that we could also find elasticities. Well, that's disappointing. So this is a factor variable, educational category. I've turned that into a factor variable. And apparently when you estimate the regression with I dot, which is a factor factor terminology. You can't do elasticities, so we'll skip elasticities for now. So in this case, what we have are average marginal effects. This is the average effect of each of the independent variables on y. We could also estimate the effect at the mean values of each of the independent variables rather than over the entire spectrum. And more fun yet, we can estimate the marginal effect for specific values of independent variables. So let me show you that one, because this one is kind of nice. So I could say margins let's do this. Suppose I want to know how the presence of children under 6 varies as the woman's age changes. Okay, and so what I could do is to say, give me the marginal effect of kids less than 6. Okay, if I just type that, I just get that one marginal effect, which we've got here. Right, when I did dy dx star, it gives me all the average marginal effects. I could just type one variable and it gives me the marginal effect for that variable. But what I want to know is, how does this change as the woman's age varies? And so I'm going to go back and modify this. I'm going to say at, and this is where it gets kind of fun. Age equals, and what are the ages? Well, before I do that, let's figure out what the ages are. So I'm going to summarize age. Then the women vary from age 30 to age 60. Okay, so let's do this. We'll say at age equals 30, 5, 60. And what that says is, I'm going to start at age 30. I'm going to increase it in intervals of 5 units at a time, and we'll increase it all the way up to age 60. Okay, and so this allows you to do a bunch of different repetitions all at once. And here's what it looks like, sort of. What did I do? I think I got my syntax. I'm gonna try that. That's better. All right, so you need parentheses around all the ages there. I left that out the first time. Okay, and so what you can see is that it uses age 30, 35, 40, 45, 50, 55, 60. And for each interval, so at age 30, the effect is to reduce the probability by almost 20%, then by 23% at age 35, at 25%. And you can see that the probability or the effect of age on probability of being employed varies depending on the woman's age. Sorry, this is the effect of number of children as the woman's age varies. And so what we're doing is looking at this interaction between two variables. And the interaction is nonlinear. because of the nature of the probit regression. And that's why if you're doing an interaction in OLS, you just multiply one variable by the other and the effect is the same regardless of the values. Here, the values have to be taken into account. And you can see that that effect, it grows and then declines. And so it's a very much a nonlinear effect. Okay. Do you have questions? Do you have any idea what I just did?
I have a question.
Yeah.
So do we interpret unit or percent, or how do we?
Well, so this is the change in the probability from a 1 unit change in X. And
Okay.
so
Unit.
if X increases by 1 year, then the probability is reduced by 0.19 or 19%. Right. So we can think about the dependent variable in percentage terms since it's a fraction between 0 and 1.
Professor, I have another question. So
Yeah.
in this case, I think it was a little bit more obvious with age, you know, that we would do an increment by 5 and have look
Yeah.
at certain age groups. And again, even in the previous example with GPA, last time, I think it made sense. But we will always be given independent variable that we know how to work with. You know, if it's like a variable that has a huge variance or something like that, how will we handle it?
Carefully.
Okay.
I mean,
So
the answer is these things can get complicated. And what I'm trying to do here, obviously, is to give you an example using a variable where you should have some intuition about what the variable
Right.
means and what reasonable values of it are. You can't always be guaranteed that you can have reasonable values. This is why maybe the best way to answer the question is this. You saw what I did. As I was about to give this command, I said, wait a second, let's go back and look at what this variable looks like, right? And so
Yeah.
based on this variable, and it's a very manageable, understandable variable, I decided to use 30 to 60 with 5-year ranges. If you go back and look at a variable and it's just all over the place, an extreme range, maybe what you do is to ask, where do 90% of the values fall? And look over that range. You know, I mean, if you have extreme outliers, they're probably not the sort of thing you want to spend a lot of time trying to base your estimate on. And so it's the further you go into this, the less you can use the cookbook, and the more you have to kind of use some reasonable judgment and intuition to guide you. And there's just no rule that I can give you that is gonna work in all cases. So when you start to understand how this stuff works, that's what makes it fun, is that you're kind of unconstrained and you can look at these tools and say, well, what can I figure out with this? And sometimes it leads you down holes you don't want to go down, and you end up with things that aren't particularly useful. But you can learn a lot if as you play with it, as you experiment. So
Yeah. Thanks.
yeah. Anybody else? All right. So let me show you. Let me show you one other thing here, and then we'll go to the question I left you with on Friday, and then we'll move forward from there. So, so I insisted on doing this regression with this categorical variable in it, the educational category. And let's do two things. One, let me go back and re-estimate this regression, but instead of using this categorical variable, I'll use the education variables that I was looking to replace, which are these. Okay. And you can see that that comes out, that regression comes out the same. But now it's just, I just have dummy variables in here. Now when I ask for elasticities, Stata will give me the elasticities. Before, I didn't like the elasticities because I had that categorical variable in, or the multi-value variable in. But if you have independent dummy variables, Stata is okay with giving you elasticities. And so now we can think, so these are also average elasticities over all ranges of values of these variables. And so what this says is that if kids less than 6 increases by 1%, then the probability of being in the labor force decreases by 0.25%. Okay. So these are all less than 1, which means they're all inelastic responses. A 1% change in the independent variable leads to a less than 1% change in the dependent variable. Age is the one variable here that has an elastic response. A 1% increase in age reduces the probability of being in by more than 1%, by 2%. And so, you know, elasticities can be useful ways to sort of judge the magnitude of a response. And it's just nice that you can get these pretty easily. Questions about elasticity? All right. So now I'll go back and use the educational category variable again. And I can, after I do this, I can say margins r dot cat. Oop, that's not what I want. R dot educational cat. And so what this does is it goes back and looks at the educational variables, and it gives me the magnitude of the effect for each one versus the omitted category. Okay, and so the omitted category was less than high school. So for a person who has a high school education versus less than high school, the probability is 0.05 higher for a person with high school. For the person with more than high school, it's 12.5% higher. For a person with a college education, it's 14% higher. And with graduate work, it's 32% higher. And these are all versus the omitted category. Okay. And so this is a nice little tool that you can use to compare to the omitted category, which isn't so straightforward to do here. Okay. All right, questions? So if you're interested in margins and the things you can find, I would encourage you to look in the manual at the margins command. And you could spend most of the rest of the semester learning about the margins command, because it does a zillion things. It used to be really simple, and every time they do another version of Stata, they add more capabilities to it, and it does a lot. I'm assuming you know how to get to the manual, which is you go up here to the help window, and it says PDF documentation. And if you click that, it brings up the whole manual as a PDF file. And it has an index. There's a ton of stuff in there. I use it all the time, but that's just how I am. Because I also have a limited internal memory capacity. Okay. So So I had given you this data set, the binary one, at the end of class the other day. And I asked you, how does the effect of GRE on the probability of being admitted change as GPA changes? And so this is asking you to do the same sort of thing we did just a few minutes ago with the age, mother's age. And so let's just bring up the data here. There's 400 observations. Admitted or admit is a dummy variable. That's going to be our dependent variable. And we're going to say that it depends on score on the GRE, grade point average, and rank in class. This is quartiles, top quartile, second, third, and fourth quartile. And so we could just, by the way, I apologize for the fact that I keep on doing Probit. It's my habit, because I'm an economist. We could just as well do Logit here. And I would encourage you to go back and maybe work through these examples using Logit. You'll see that they're a little bit different. They're not going to say much of anything that's different. They're always very close to each other. All right, so Probit. Actually, you could do GRE, GPA, I dot rank. Okay. And so this says that a 1-point increase in the GRE increases the probability of being admitted by less than 1%. The GRE is generally not greater than 1-point increments. So a 10-point increase would be a little bit more than a 10-point increase in the GRE would give us a 0.013 increase in the probability of being admitted. A 1-point increase in GPA increases the probability of being admitted by 47%. And you can see that compared to the top quartile, being in the second, third, or fourth quartiles reduces the probability of being admitted. Okay. And so if you're in the second quartile, it reduces the probability by 15% compared to the top quartile, 28% compared to the top quartile, or 32% compared to the top quartile. Okay. So I had asked you, how does the effect of GRE change as GPA changes? And so to get at this, we would say margins dy dx GRE that's the marginal effect of the GRE. And I want to know, how does that vary as grade point average varies? Or how does that change as grade point average varies? I'll go back up here to my summary statistics, and I can see the GPA goes from 2.26 to 4. So maybe what I'll do is this. I'll say, what's the marginal effect of GRE at GPA equals 2.5, 0.5, 4. And so we'll go from a GPA of 2.5 to a GPA of 4 in half unit or half point increments. What happened? Why did it do that? You don't know.
Should
I don't
we
know.
put in as 0.5 increments?
0.5.
Oh, thank you. Yeah, thank you.
No,
That's better. Okay. And so here we get the marginal effect of GRE. So if you think about the GRE going up 100 points, if your GPA is 2.5, a 100-point increase in the GRE will increase your probability by about 3%. At a GPA of 3, it increases it by about 4%. At a GPA of 3.5, a 100-point increase in GRE increases your probability by 4.6%. And if you have a GPA of 4, a 100-point increase in GRE increases your probability by about 5%. Okay. And so that would seem to make sense. Okay. Questions? All right. So so there are almost literally an unlimited number of things you can do in interpreting these regressions with dummy variables as dependent variables, just because of the nonlinear nature of the estimators. And I don't want to go too far in these things because when they're all hypothetical, it's hard to keep track of them and to see what they mean. What I would encourage you to do is to, as you're working on a problem, to be inquisitive, to ask questions, do as much as you can to figure out what the answer to your question is, and be be sure to ask questions whenever you have them. I simply can't do everything here, so what I want to do is to move on to the Tobit regression, and Tobit is kind of interesting. So I'm going to stop that. And so the Tobit regression is it's a sort of a hybrid regression. It's a hybrid because the dependent variable in a Tobit regression is what we call a censored variable. Okay. And the variable is continuous, like what you would do in ordinary least squares, but it's censored because you can't observe it beyond some value. So what does this mean? So Tobit is invented by a guy named James Tobin. Anybody ever heard of Tobin? Does anybody know who Tobin was? All right, wait, hold on one sec. Okay, so I say, does anybody know who Tobin was? And you say,
Economist.
oh, come on. Am I getting no sound here? Oh, there we go. This is a lot of work for very limited payoff. My cricket sound effect is just not working. So Tobin was an economist. He was at Yale, and he won a Nobel Prize in economics. Did a whole bunch of really important stuff. And in the late 1950s, Tobin, he got the Nobel Prize in '81. He died, I don't know, sometime in the mid '90s. He was an interesting guy. In the late 50s, he is when he invented the Tobit estimator. And the problem he was working on, and I think he was doing this just to entertain himself, was he was working on the demand for automobiles. And what he figured out is this: if you go out and you collect data on how much people spend on automobiles, you get a lot of people who have bought an automobile and they've spent however much, 5,000, 10,000, you can observe how much they've spent on an automobile. And you get a bunch of people who spend zero. And so the problem seemed to be that there are some people who would like to spend $30 on an automobile. That would be their desired amount, but there's no such thing as a $30 automobile, and so they end up spending zero. And so what he's trying to do is to estimate the quantity demanded, or how much people would like to spend on automobiles. And he's got a bunch of zeros, and the question is, what do the zeros mean? Do they all mean people literally don't want to spend anything, or that there's simply nothing in the marketplace that they can purchase, and so they end up at zero? And so the problem is that you've got, theoretically, the design, how much you want to spend is a continuous variable, but it gets cut off at some point because there's simply no observations below that bottom end. Okay, and so you can have a variable that's censored from below, like that one, where you don't see any values below some value. You don't see any observations below some value. You can have a variable that's censored from above, where you don't see any observations above some value. This happens actually, censoring from above in most data on individuals is collected in the US, particularly like the census or current population survey, or the longitudinal data sets we've looked at. Those data sets, they often contain geographical information to tell you if a person lives in what state, if they live in an urban area, and you can kind of narrow down where they live. And they also ask people for incomes. And what they do is they set an upper limit on what income they'll report in the data set. And the reason they do this is that if you actually report people's actual incomes, and you have a geographical area that's fairly limited, and you report that there's one person who earns $14 million a year, you can figure out who that one person is. And what they want to do is to protect the privacy of the individuals they're collecting data from in these public data sets. And so what they'll do is they'll cut off income at some value, maybe $200,000. And anybody with an income above that is simply coded as 200,000. And so now you have, if you want to figure out what determines people's incomes, you have this variable which is continuous up to $200,000, and above that, everybody's just reported as 200,000. And so that's censoring from above. Okay, and in either of those cases, you might use Tobit estimation to try to deal with this kind of censoring problem. So let me talk about the censoring issue and why it is a problem. Okay. First, let's just talk about why you need a special method to deal with this. Let me change cameras and I'll, all right. All right. All right. So, so imagine that you have data set. And what the data actually look like, or maybe something like this. All right. Each one of these things is an observation. Okay. And if we draw a regression line, this is a OLS regression through that data set, it's going to look something like that. Now suppose that at some level, call this Y star, we can't observe any values of Y below Y star. Okay, so each of these values that happens below Y star ends up just being pushed up to here. And our data set then looks like this. And omits these values down here that we can't actually observe because of the censoring. So we get censoring at this value of Y star. And if we just do an ordinary least squares regression on the data that we can actually observe, that regression is going to look more like that. So this is OLS on the censored data. And this is OLS on the actual data. Well, the actual but unobserved values. That makes sense? So if you could actually observe all of these values, you might get this regression line. But when you collect your data, these values are invisible and you end up with this regression line. And this is a biased regression. This is what you would actually like to be able to see. The one in green is what you would prefer to see. The one in purple is what you end up with. And that bias is what the Tobit regression is supposed to deal with. Okay, that makes sense? All right. So how to frame this? So the challenge for us at this point is to kind of frame this as an economic issue and not just a statistical issue. And so let me just set the problem up. I think what I want to do is just to set the problem up today, and then we'll come back on Friday and try to work through how this estimation works and what the various issues are that come up. So suppose we're interested in spending on tobacco products. Oops, products. in households in the US. In a particular year, say. And so let's do this. We'll say let Y equal expenditures on households, I'm sorry, on tobacco. Let Z equal expenditures on all other goods. And so that's a common trick that economists like to use, where we have the variable we're actually interested in versus all others. We might think of this as a composite commodity when we lump all those other goods together. And the rule is that as long as the relative prices of all those other goods don't change, we can do this. We can lump them together, and that's legal. And let's make W total income. Okay, and so as economists, we want to think about this as an optimization problem, a utility maximization problem. And so, so we'll say this, that we're going to characterize this in the following way. The household's problem is to maximize utility, which is a function of expenditure on tobacco and expenditure on all other goods. Oops, that should be Z on all other goods. Subject to the constraint that Y plus Z have to be less than or equal to W. Can't spend more than your income. And Y and Z have to be non-negative. Okay. So what are the possible outcomes of this model? Well, it's unlikely that Z equals 0. Right? It's unlikely. Z would equal 0 only if a household spent their entire income on tobacco. Okay, so that seems unlikely. It's unlikely that Z is 0, so that's not a concern. However, it is very likely that Y equals 0 for some households. Okay. This is a corner solution. Okay, and so if the household is engaged in a utility maximization problem, we know that corner solutions where you consume all of one good and none of the other are always a possibility. In this case, we're not going to be concerned about a corner at Y equals W, where Z equals 0, where you're not consuming anything but tobacco. But we are interested in a corner where Y is 0. And if Y is the dependent variable, the thing we're trying to explain, because we're interested in spending on tobacco products, then we have to account for the possible corner solution here. Okay, and so So for me, one of the things that I always think is fun about doing this kind of econometrics is that you come up with ways to actually measure or count empirically for these theoretical things that come up in microtheory, and you think there's no way to actually deal with them, but in fact there is. And so Tobit regression is really meant to deal with corner solutions like this. Okay. And so in this case, what does it mean if y is 0? Well, it could mean a couple of things. It could be that people would like to spend 4 cents on tobacco, but that's not really an option, so they end up spending 0. It may be that they have some sort of philosophical opposition to the tobacco use, and their actual desired spending would be even negative. Well, there's no such thing as negative spending here, so they end up at 0. And so, so y is the observed level of spending. And y star is the desired level of spending. And the two may be different from one another. So when you go back to Tobit's model of spending on cars, right? If you'd like to spend $100 on a car, but there's no such thing as a $100 car, or at least not one that moves. And so what you end up with is someone who actually spends 0. Okay, and that's what you observe, even though what you're trying to estimate is how much people would like to be spending on cars or tobacco or whatever the product happens to be. Okay. So the solution to the utility maximization problem is y star. That's how much people would like to consume of y. And that's going to be estimable as a regression. Okay, so we could estimate what determines the amount of spending y star. The problem is that not all values of y star are observable. So let me just sneak that in here at the bottom. And so we might say that y star is a latent variable. Okay. We know it's there, but we can't really observe it in its entirety. So we'd like to estimate the determinants of y star. but we only observe y and so we estimate so let's say this, our model becomes the following when we limit ourselves to what we can actually observe. Yi equals beta naught plus beta 1 xi plus epsilon I. Yi equals y star if y star is greater than 0, and yi equals 0 if y star is less than 0. So we have a model, it's a regression model, where we observe some values of the variable we're really interested in, but other variable values are not observed, they are censored. Okay, and so this describes censoring at y star equals 0, well, less than or equal to 0.
Professor,
Mm-hmm.
I have a question. So here, y star is the actual with the unobservables, right?
Correct. It's,
Okay.
well, so it's observable some of the time and unobservable some of the time.
Yes.
Right? And that's what makes
Okay.
it interesting, right?
Okay.
And so this is the model that that Tobin gets interested in, and so this is Tobit regression. This is the basic setup for Tobit regression, and I just write this down to emphasize what's going on here. This is essentially a hybrid model. When y star is observable, it's just ordinary least squares. But part of the problem we have to figure out is when is it observable and when is it not? And that's a lot like a probit regression, right? Observable, unobservable, zeros and positive values. So in probit, we have zeros and ones. In Tobit, we have zeros and continuous variable above some level. And so this initially, this is called Tobin's probit because it was sort of this strange application of probit regression, and eventually has come to be called Tobit. And and so there are several questions that we want to try to get out of this, or try to ask and try to get the data to provide information for us. One, we want to know what is the probability that yi is equal to 0, or the probability that it's not equal to 0, right? So that's very much sort of a probit question. So it's either 0 or it's greater than 0. Second, we can ask, let's see. What is the expected value of y given or conditional on being uncensored? So if we just restrict ourselves to these values that we can observe, what's the expected value of y there? We might ask, oops, what is the expected value of y star, the latent variable? It would be nice if we could get an estimate of that, since that's the thing we're actually setting out to estimate to begin with. And one other thing. And the fourth thing is, what is the expected value of y given it is censored? So we want to know about y conditional on being uncensored, y when it is censored, what is the expected value of the latent variable y star, and what's simply the probability of having a censored observation versus an uncensored one. Okay. And so I always think Tobit is kind of an interesting estimator because it gives us all kinds of information, and the hybrid nature of it, I think, just makes it interesting. So sorry if I scared you. So what I want to do is we kind of set the model up. And what I want to do is to stop there because I'd rather not have to cut myself off midstream trying to explain how this thing works. So on Friday, we'll come back and talk about how the Tobit model works, what it's actually doing, the different pieces of information we can get out of it. Just a little bit of a trigger warning, there will be a little bit of statistics involved. Okay, so if you've had bad experiences with statistics before, I'm just telling you, you know, that's what's coming. So brace yourself. Try not to make it too ugly. Okay. Questions or anything? All right. So what I would encourage you to do is to take some of the data that you've got, play with it a little bit, mess around with probit and logit estimation, try to get yourself comfortable with it. And if you have questions, I'll be happy to take questions beginning on Friday, and then we'll go into the Tobit model. And right after that, I'll give you a lab to do. If I'm not too busy quarantining, the lab will be ready to go on Friday. And otherwise, I'll send it to you when I have it ready to go. I kind of want it to be good to go. So anyway, all right, stop there. Everybody keep having the time of your life. Elena?
Professor, sorry.
Yeah.
When are you thinking the lab will be due, more or less?
When will it be due?
Yeah.
My plan is to give you somewhere between 20 and 45 minutes to complete it.
Oh, perfect.
So
you were gonna say 20 and 45 days.
Well, let's just see. I'm just looking at my calendar here.
Yeah. Just to remind you that somebody has a thesis due in a little bit. So.
Pardon me?
No, just saying that some people have some thesis due in a little bit. So if you can give us a little, time ahead.
What, you have a life?
A thesis.
A thesis. That's not life.
No, it's not. I know. Tell your other your other colleagues.
Yeah, no. Okay, so today is the 8th.
Yes.
How about this? I mean, I don't have strong feelings about this. My objective is actually not to make your life worse. I know it's hard to tell sometimes, but and so let me give it to you. You can take a look at it, start to work on it, and then we'll figure out a due date that works. Okay?
Yeah. Yeah, that'd be good.
Obviously, I would prefer not to be teaching this way. You'd prefer not to be learning this way. And my expectation is that doing it this way is just going to be slower. And so the temptation is to say, get it done quickly so we can do another thing before the semester ends, which I'm happy to do, but if this is the last thing we do and you simply work on the lab, turn it in, and we're done, I feel like my summer is going to be just as good either way.
Okay. Nice.
So, so that's it. I mean, I don't have strong feelings. I'm happy to do whatever is going to work best for you. Okay, unless, I wish this semester was going a different way, but I'm happy just to get it over with.
We all are, I think, at
I
this
know.
point. But
So, other thoughts?
Thank you.
Options? Yeah. All right. So, we'll be back, same bat time, same bat channel. You probably don't even know what that means, do you? So Batman used to be this show when I was like in elementary school. There was a Batman, that was a live action television program. And at the end of the show, they would always say, we'll be back next week, same bat time, same bat channel. And so if you find someone my age and say that to them, they'll know what that means. And here I am, just educating. That's what I do. All right, I'll see you on Friday. Thanks for your patience. Be well. Take care.
Thank
you,
Thank you, Professor.
Thank you, Professor.
you.
Yep. Bye-bye.
Bye.
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 Bye-bye.